Donc, on va commencer par l'exposé d'Andras. Bon, Andras, vous le connaissez certainement, donc je ne vais pas vraiment rester longtemps pour... C'était un grand plaisir de l'introduire pour cet exposé, pour cette présentation. Andras, il est du laboratoire SPOC à Grenoble. Il est maintenant chercheur émérite. Voilà, il a beaucoup travaillé, donc il est fatigué.
Depuis 2 semaines. Depuis 2 semaines.
Depuis 2 semaines, voilà. Tu vois, donc on le prend, nous, voilà. Il a décidé de se reposer parce qu'il a beaucoup travaillé. Et voilà,
pas
mais
du
nous,
tout.
on va pas le laisser.
Je n'ai pas tellement travaillé et je n'ai pas décidé de me reposer.
Voilà, on le laisse pas se reposer. Donc, c'est pour ça qu'on l'a pris directement comme ça pour qu'il nous fasse cette présentation. Andras, c'est un très grand chercheur. Il est parmi les grands spécialistes et les premiers chercheurs en optimisation combinatoire et programmation mathématique et théorie des graphes. Il a un scope vraiment très large de recherche. Bon, qui couvre tout ça, mais aussi un peu les polyèdres, la combinatoire polyédrale, la combinatoire en général, les algorithmes d'approximation, bon, bref, la programmation linéaire, programmation nombre entier, etc., les mathématiques discrètes, donc tout. Il a un large record de production scientifique. Honnêtement, moi, je suis allé pour voir un peu, je n'ai pas pu compter. J'ai compté, après j'étais très fatigué. J'ai laissé tomber parce qu'il a donc un nombre très grand de publications. Ils sont toutes des publications vraiment qui sont publiées dans des top journals, dans les premiers journaux du domaine. Voilà, donc bon, c'est vraiment donc c'est une grande référence à laquelle on doit revenir pour toutes les questions donc liées à ces domaines-là. Aujourd'hui, il nous fait vraiment l'honneur. Andras, comme toujours, honnêtement, Andras, il est toujours à nos côtés depuis des années dans ce groupe POC, dans les JPOC, dans beaucoup dans ISCO, dans beaucoup il nous prête main forte et après, il vient enrichir avec sa science les exposés, les présentations et les activités du groupe. Donc, au nom du groupe, et je voudrais vraiment à cette occasion le remercier énormément. Merci beaucoup, Andras. Aujourd'hui, il va nous parler de Uniform Covers for Cons and Combinatorial Problems. Voilà, merci beaucoup, Andras, et c'est à toi maintenant la parole.
D'accord, merci beaucoup, Rida.
Je lui ai demandé de présenter en arabe. Il m'a dit l'arabe, donc non, c'est la prochaine fois. Peut-être qu'il essaiera. Voilà.
Oui, j'ai proposé le hongrois. Bon, j'ai essayé de m'enfuir. I tried to escape, but Rida convinced me with very strong arguments. I tried to escape, first of all, because, as Ivana said, promised in her introduction, we'll speak about our most recent results. And my most recent results are not directly related to polyhedra. So I tried to escape with this, but then Rida said, oh, no, it's not a problem. You just speak about your last talk. I was just in Bonn last month. So this emeritus status made me more busy than usually. And I really wanted to have a little work on my ease, on my things that I wanted to work on. And but then Rida said I can just choose the subjects that were planned 2 years ago at this canceled, postponed GPOC meeting, which was canceled actually not because of COVID yet, but because of a strike. So we postponed it, and we will have it now. So I did indeed. I have kept the subjects that I was planning for that meeting, and I prepared a bit, I refreshed it, and I realized that many things happened in the past 2 years also related to that subject. So it was a pleasure to prepare this talk. And okay, so the subject is uniform covers. which is a very simple thing. A uniform cover is a family of multisets. So every set in this family, in this hypergraph, has a multiplicity, and with the property that every element of the base set is contained in the same number of elements of the family. Every point is contained in the same number of elements of the family. In other words, if you sum up the characteristic vectors of the elements of the family, you get a constant vector. And if you divide, you get that the all-one vector is in the cone of the characteristic vectors of your set. And conversely, if you are in the cone of the characteristic vectors of your set, you multiply by the denominator and you get a uniform cover. So you just, when the all-one vector is in the cone of the characteristic vectors of sets. This is just about that. And it will give, I will show various examples. Let us, 5 examples I have chosen. There are many. And actually things that we are working on these days, the integrality gap, duality gap of combinatorial notions, which do not include polyhedra, can be interpreted in this way too. I have chosen 5 examples. And you will see that on these 5 examples, they have meaningful things to say, these uniform covers. And even about aspects that I will not discuss, like algorithmic aspects. I will follow Michele in that I won't speak much about computation, but you can put questions. In the discussion part, we can speak about computation. Some things are related to computations, some of the things I will speak about. So the first will be uniform covers by triangles, it's edge sets. The second will be stable sets, uniform covers by stable sets, then matchings, then packed bins, and finally by tours, graphic TSP tours. Okay, let's start. So triangles. So you have here 2 graphs. And yeah, I forgot to say that you can interrupt me at any time, because Rida, to convince me, also said that time will not count. We can have more time. So just interrupt me. We won't take until Francisco's talk.
No problem, no problem.
Okay, I would like to see some of you. So you are all hidden, which is, it's much better if some of you can be seen. Thank you, Rida, thank you, Maurice. So you have here 2 graphs, and both of them have some triangles. What do you think? And you can raise your hands. I'm not sure I will see it, but Rida will see, I'm sure. In which one can the edges be uniformly covered by the triangles? Can in both, one of them, or neither of them? Can we cover the edges by triangles? Okay, I'm sure many of you know, many of you see that on the left figure, you just take the sum of all triangles, and every edge will be covered by 2 triangles. So on the left figure you can, and on the right figure, can you? It looks like hard because there are some edges which are contained only in 1 triangle. So you can't cover all edges, but can you explain what is the certificate for that, for not being coverable by triangles? Okay, so in other words, is the all-one function in the cone of triangles in these graphs? I will tell some motivations afterwards, but it's in itself, I hope, a meaningful problem. So is the all-one function in the cone of triangles? Yes, on the left figure, you just take 1/2 times the sum of all triangles, and it is. And on the left figure, why isn't it? Now I will tell you a reason. I will tell you how to certify this. Of course, on this example, you just check. There are many ways of justifying that you have only that you don't have. that the O1 function is not in the convex hull of triangles, but I will show you an inequality. We are at GPOC, so I will give a polyhedral reason why this graph on the right cannot be covered uniformly. The O1 function is not in the cone of triangles. It is because the following inequality, you put -1, here is a graph that can be hard. Can you see the graph on the right down corner? You have some coefficients, and that's the vector A, which is in the condition above. So AX at least 0 is feasible by all the triangles. Why? Because the -1 edges form a graph that doesn't have triangle. That's a triangle-free graph. That's C4. It doesn't have any triangle. So if you put -1 on its edges, it doesn't have any since it doesn't have any triangles, you must have at least one edge of the induced graph, or at least two edges of the co-boundary in order to form a triangle. So if you put these coefficients, so 2 on this induced edge of the graph, which is not in among the red edges, and 1/2 on the edges that have one endpoint in the graph and the other endpoint not in the graph, then this condition A has scalar product at least 0 with any triangle because of the property that I just mentioned. On the other hand, R vector -1 on 4 elements, 2 and 1/2. If you multiply with this vector, it gives -1, which is smaller than 0. So all triangles are at least 0 on this vector, and R vector is negative, so it separates R vector from the triangles. R graph vector, the O1 vector, it separates the O1 vector from the triangles. So the O1 vector is not in the cone of triangles. Okay, now this problem, I will tell you the history of this problem. I forgot about this wonderful laser, which I have. But yes, this was our subject of talks, of discussions with Svatya Polyak, who died in a car accident in 1995. And he brought the problem actually from regular covers by triangles, which he heard actually from Tuza, who with Milici had already some work, but not published yet. It was published in 94 first, the first Milici-Tuza paper. And now when I prepared the talk, I saw that there are papers still in 2021 about these uniform colors by other small objects like triangles, small graphs or several graphs. So there could be a lot of work for us because Milici and Tuza are graph theorists, and they, even if you speak to them about, and I did so, about cones, they will forget. In none of their papers the cones appear, although they are about this. They are about characterizing when the O1 vector is in the cone of their combinatorial objects. So then I immediately liked the problem because I reformulated it in terms of cones, and I had several trials of conjectures with counterexamples, and actually Paul Seymour in chats and at parties also discussed with us about this. So we stated a problem in the problem part of the graph structure theory book. At the end, there is a collection of problems by Nate Dean, and this problem was published there to characterize graphs which can be regularly covered by triangles, reformulated to cones. And here is the reformulation to cones, which is just the generalization of what we had here on the slides. Here is this is a screenshot from the volume, a scan from this Graph Miners volume, The title is not graph miners, but graph structure theory. It has nothing to do with graph structures, but it had to do with our hobby during this meeting. And the conjecture is still open. Nobody, probably people who would have been interested in, like these graph theorists, do not know enough about it, and or do not know that this would solve their problem in some sense, and other people didn't get interested in it. So I state it for you here. Some of you may get interest in looking into this conjecture and looking to other combinatorial objects, determining their cone, and determining then when the OR1 vector is in their cone, you would get results that can be translated for graph theorists, and they would be interested in. But we can't stop here. We go to another problem about stable sets, coloring. The coloring and covering by stable set. What is a covering by stable sets? That's a fractional covering. If you fractionally color, if you integrally color, it's just a coloring problem. And in H-perfect graphs, for which we know the stable set polytope. So a graph is called H-perfect if the clique inequalities, so the sum of the variables is at most 1 on every clique, and the odd cycle inequalities, which means that the sum of variables on every cycle, on every circuit, is at most, every odd circuit is at most half rounded down of the cardinality of that circuit. So you see the inequalities here, and the graph is H-perfect if these inequalities determine the stable set polytope. Equivalently, if this is an integer polytope. When the maximum clique size is 3, then these graphs are called T-perfect. Hard to remember, not so logical. Why one H? It's whole perfect. The other is T perfect. Actually, people in Grenoble, Jean-Pierre Uri and his students of the time, maybe Najib Asbi, Rida will know more about it. Gave these names: true parfait and whole perfect. True is when it's more, when maximum clique size is 3. Okay, so now when the OR1 vector is in the cone, well, it's always in the cone because you have small vectors here. I had on my first slide, I didn't say it orally, that sometimes, like in our first problem on triangles, we want to know when the OR1 vector is in the cone. Or in some other problems, we want to minimize the sum of coefficients in the cone. That is, we want to divide by a constant to bring ourselves to the polytope. So here it is the second kind of question that arises. The OR1 vector is always on the cone, but we want to minimize the sum of the coefficients of the stable set, which have the OR1 vector as a result. And actually, this is clearly the fractional chromatic number. And when we want this to be integer, I said it already, then this is the chromatic number. Now, the anti-blocker of this polyhedron is the polyhedron where the constraints are stable sets. So you want to sum your variables on stable set and be at most 1 for every stable set, and you have non-negativity constraints like in this green line. So at most 1 on every stable set. What are the vertices of this polyhedron for H-perfect graphs? We all know from Farkas's work, and quite easy to check by Farkas's lemma, that the vertices are just what were the constraints previously, but you have to normalize to make the right-hand sides 1. So the vertices of this polyhedron are the origin, characteristic vectors of cliques, which were here are constraints, and circuits divided by the right-hand side. So circuits of size 2k plus 1 divided by k. Now, if you want to maximize the size of the objective function 1, on this polyhedron, the cycles will give a value always smaller than 2.5, between 2 and 2.5. It's only cliques of bigger size that will bring you to bigger sizes than 3. And okay, this I said already. And if it were true that we always have a 3 coloration, so we always have 3 stable sets. But by the duality theorem, fractionally, the dual solution, the dual optimum, the dual minimum for the sum of coefficients to get 1 will be always the maximum primal solution, and that we know what is the maximum primal solution, 2.5, or the maximum clique. But is it possible that we are so lucky that for H-perfect graphs, the integer solution is always equal to the fractional solution? So for this, we would have to have omega, or when the maximum clique is 3 coloration. And this is not so trivial to find a counterexample to this. It is trivial that if you have a T-perfect graph, then the fractional chromatic number is at most 3. I just said why. And Bruce Shepard had a conjecture in the early 90s that if a graph is T-perfect, then the chromatic number is also at most 3. So, Bruce told this problem to several of us. And what happened is that he also showed to Monique Laurent and Paul Seymour, and they realized that if you take the complement of the line graph of a prism, that's a counterexample. It's actually quite natural, because what is the complement? It looks like making a complement of line graph. But this just means that you want to cover with cliques of the line graph. So forget about complement, cliques of the line graph. That means that you want to have a vertex cover of the graph itself. So what does it mean to have a maximum clique of the complement of the line graph? It means a maximum stable set of the line graph, which means a maximum matching. Well, in this graph, the maximum matching has size 3, and the minimum cover, it's well known, it doesn't have the Koenig property, the minimum cover is 4. And the fact that it is T-perfect is also very natural, because we know that because we are speaking about matchings, right? About matchings of this graph, and matchings are described. We know very well the matching polytope, and with blossom constraints. And this is not a very complicated graph. So the blossom constraints become odd cycle constraints. So it's a T-perfect graph, and it doesn't have this property. It is not three colorable, although it is T-perfect, and the maximum clique is 3. Then later on, these logical justifications have led Johan Benschetrit, who was my student, to realize that there's another graph which has this property, the complement of the line graph of the 5-wheel, and for the same reason. And probably in some sense, these are the only two graphs, and Actually, in some quite restricted sense, Johan already proved that these are the two ones in among some subclasses of graphs, but maybe more generally also, these are the two graphs that play a role. And what do you do when there are counterexamples to a conjecture? So when there are such bounds, then you do the silly thing that, okay, they are not 3 colorable, but maybe 4 colorable. Well, not a great idea. Looks like when you have courses, there are always, when you have a counterexample, there will be students who will say, well, but then let's add a condition, and then there is a spiral. But here, maybe there's more into this spiral, because it would imply, if they would be 4 colorable, it would imply that any H-perfect graph is omega plus 1 colorable. Moreover, this omega plus 1, this plus 1, occurs actually quite often in combinatorial problems, as we will see. We will see other examples of this plus 1. You have the integer decomposition or integer rounding, depends on from which side you look at it, property. When you have equality with this more natural bound, that would have been the case if Bruce's original conjecture would have been true. And this plus 1 occurs quite a lot. This is called the mirror property, modified integer rounding property, and we'll see several examples of this. So every H-perfect graph, H-perfect graphs, the stable set polynomial of the H-perfect graph would belong to this integer rounding property case. Yes.
C'est Denis. Je comprends pas, le prisme, il n'est pas 3 colorable.
Comment? Le prisme, il est 3 colorable, mais je parle du complément du line graph du prisme. Je croyais que le son est parti, j'avais déjà peur d'un problème technique.
Non, non, pardon, ok,
Complement, this is, c'est un twist. Est-ce qu'il y a quelqu'un qui ne comprend pas? Bon, I will continue in English for any case. Yeah, I know some of you who are, because Francisco is not yet here, right? Francisco also speaks French, of course. He was a student in Grenoble. Okay, so complement line graph, there the stable sets are the matchings. Wait a second. Yes, complement of line graph. So the the stable sets are the stars of vertices. In the line graph, the cliques are the triangles and the stars of vertices, right? And so in the complement of the line graph, the stable sets are the stars of vertices in this graph. So in other words, that's or triangles. So in other words, the chromatic number of the complement of the line graph is essentially the minimum vertex cover. Who asked the question? I didn't see you. Do you hear me?
Oui, tout va bien.
Yeah, yes, we are hearing you. No problem, Andras.
Yeah, yeah. So it is the vertex. Yeah, yeah. It is the vertex cover, which is the chromatic number of the complement of the line graph, and the stable set, and the maximum clique, because we are comparing the chromatic number to the clique number, and the clique of the complement of the line graph is the matchings of the original graph, right? Each matching is a stable set in the line graph and is a clique in the complement of the line graph. So we are comparing maximum matching to minimum vertex covers. The maximum matching is 3, the minimum vertex cover is 4. And that's the chromatic number of the complement of the line graph. Is it okay? Did I answer the question? I don't see who asked it. Anyway.
No, I didn't hear a question. No, it's fine.
Okay, okay. So maybe I don't know. Okay, okay, and now if you just extend by 1 from 3 to 4, you are having a conjecture that implies for H-preferred graphs that they are omega plus 1 colorable. And this conjecture by a postdoc that we had here, Henning Brun, and he liked very much the problem and worked on it, and later on Johan Benschetrit as well. And they have results in particular cases like low-free graphs. So for instance, for line graphs, this conjecture is true. Just the idea, because that's very polyhedral idea, why this conjecture for 3, and then we also see some results, some proof that I associated with this conjecture to promote it. It is a proof like Fulkerson's half proof for the perfect graph theorem. Since the graph is H perfect, when your maximum clique is bigger than 3, then all these maximum cliques lie on a face. So when you maximize the size in a dual solution, there will be a stable set. Since your graph is H perfect, there will be a stable set meeting all the maximum cliques. And if you delete this stable set, which meets all the maximum cliques, then the clique size decreases by 1, and you can do induction. So you can reduce everything actually to the triangle-free T-perfect case. So T-perfect graphs which don't have triangles are 3 colorable. This is the main conjecture that probably involves graph theory, and that is proved for particular cases by these people. Okay, and this is a Mirup case. Mirup because we don't have the integer decomposition property, whatever it is. It's not essential that we state it. It's just that one more is true than what would be the nicest. That we'll see more today. And as I said, some recent work that we are doing for about the key boundedness and integrality gap is also related to this. Can also be stated in this way, in this Mirup way. You have sometimes what you would expect, so +1 in your results. Okay, let's see a new case of this. So you can always, if you are lost, you can always start anew for our 5 subjects. Let's look at matchings. You have these 3 houses that you have to supply with energy, and you can choose between wind, gas, and nuclear energy, and each has some costs. Now, I will state an exercise, and it is that there exists a perfect matching in this graph with costs at least 1/3 of the total cost. Or at most 1/3 if you want, because here we are speaking about costs, we want small costs. There is a perfect matching at most 1/3 of the total costs, which costs at most, I should have written. Why? Why? Can somebody tell the reason? I'm sure yes. Well, there is this Koenig edge coloring theorem. This is a cubic graph. Every vertex has degree 3, so you can 3 edge color it. And so one of the matchings will be of size at most 3. So let's make things more complicated, and we'll probably have the reward that it is worth. So this was the first solution from Koenig's edge coloring theorem. And the second proof will be polyhedral. Well, we know that the matching polytope for bipartite graphs, and the perfect matching polytope is when you require here equality Didn't I state it? No, I didn't state, but the perfect matching polytope for bipartite graphs is this, but you have equality here for every vertex. The sum on every on the star of every vertex is equal to 1. And this bipartite matching polytope and polyhedra in general, when you take the convex hull, there are actually 2 other languages that you can use, and I will use these languages. So let me introduce it here. You can say that a convex combination is a weighted average, right? You multiply and you divide by the sum, then you get a convex combination. So that's a weighted average. And a weighted average can also be interpreted as a probability distribution, that in your convex combination, each element is a random choice, and the coefficient of your combinatorial object, the coefficient is the probability of choosing it. Then the mean value is something, the set of mean values is the polytope, is the convex hull. Okay, now having made things more complicated, let's see the solution too. The constant 1/3 function on the edges is in the convex hull of matchings in this graph, right? 1/3 everywhere is in the convex hull, so it's in the average of matchings with some probability distribution. So at least one of the matchings has weight, at most 1/3 of the weights. Okay, this is, we didn't go much, we just made things more complicated so far, but let's go to more general problems than just this graph. Is the same true for non-bipartite graphs? Well, something is true under one more condition. You need bridgeless, besides being cubic. Bridgeless cubic graph has a perfect matching. This is 1800, sorry for 1891, not 900. It has more than 100 years, this theorem. What is a bridge? A bridge is above, and in a graph, a bridge is just a cut edge. If you delete the edge, then the graph has 2 components. Okay. Peterson's theorem is not true. This is the well-known example, probably given by Peterson, that if you don't have that if you allow bridges, then you don't necessarily have a perfect matching. Now, again, the convex hull of perfect matchings of an arbitrary graph, we know from Edmonds, is described. You have to add some odd cut inequalities, and now again it follows that the 1/3 vector is still in the convex combination of matchings, right? Because the 1/3 vector under these conditions is in the polytope. 2-edge connectivity is sufficient, because if you have an odd set, it would mean that you will have at least 3 edges in the cut it determines. So is it useful? So could we prove it in another way? Maybe we could prove it also in a fully combinatorial way, that we have perfect matching, yeah, and it certainly has combinatorial proofs using, for instance, Sut's theorem. Peterson's theorem have some combinatorial proof, but is it still true that at least 1/3 of the edges, that there exists a perfect matching with at least 1/3 of the edges? Well, you could think here is a non-bipartite graph where we have, where we do have an edge coloration with 3 colors. Here it is, as our colleague who have put the previous questions remarked. So indeed, of course, well, not of course. So this one does have 3-edge coloration. So for this graph, yes, we can use an edge coloration to say that at least 1/3 of the edges is that we have a perfect matching with at least 1/3 of the total weight. But here's the Peterson graph, where we know very well that it can't be 3H colored. And here's a weighting on the edges. The small edges in the middle, are all 14. So if you sum up, I'm sure that some of you can quickly sum up. The sum is 180 of these edge weights. And if you take just perfect matching at your ease, it will be bigger than, if we have more than 60. The weight will be more than 60. On the other hand, there is another matching which has weight less than 60. So can we say that, can we extend our, it's a kind of extension of Peterson's theorem. If you define non-edges in a graph with an infinite weight, then the existence of a perfect matching means that you have perfect matching 1/3 of the total number of edges. At most 1/3 of the total number of edges means just a perfect matching in your original graph. But is it true for arbitrary weights for non-bipartite graphs? Yes, because in a cubic non-bipartite graph, there is a perfect matching because of the same reason, from the polyhedral reason. And for this, I don't know any non-polyhedral proof. So this is a generalization of Peterson's theorem. In a bridgeless cubic graph, you have weights on the edges, and there exists a perfect matching, which is of weight at least 1/3 of the total weight of the edges. Because the 1/3 vector is in the convex hull, it is an average, and so there exists a matching which has at most this weight. Okay, and similarly, if you don't have a cubic graph, but an R graph, which was a lot studied by Seymour for their edge coloring, there exists always, and their edge coloring is not at all easy, but just to have perfect matching, which is at most 1/4 of the total weight, you can just use this polyhedral argument. In an R regular graph, where the cut of every odd set is at least R, you have a perfect matching of weight 1/R of the total edge weight. Okay, now uniform covers by matchings. Let's continue. These were already uniform covers, but let's make one more remark about their coloration again. So now again, writing the all-one function as a conic combination is just a fractional coloring, and as an integer combination, it's a coloring. Here is the fractional coloring in polyhedral terms, and here is the chromatic number in polyhedral terms. Now, the reformulation of the fractional chromatic number is just what is the smallest number k for which, so yeah, because we know the polytope, right? I didn't repeat it here. I'm sorry. Yeah, here it is. The matching polytope has two kinds of constraints. One of them belonging to every vertex, the other to every odd set. And so our problem, as we mentioned already several times, is to find the minimum k for which dividing the all-one vector everywhere, you get into the matching polytope. Now, the first is a degree constraint. The first type of constraint of the matching polytope gives you that your k must be bigger than the maximum degree of your graph. But the second constraint gives you that you have to divide your characteristic vector of your constraint by the right-hand side. that should be the k in order to have the all-one vector divided by k in the polytope. Now, if you take this second number, when you don't have weights on the edges, just the all-one weight is almost the average degree. So it won't be very different from this. And this is why the fractional version of Wissing's theorem can be true. So only the degrees count. But when you put bigger weights, then graph theorists prove all kinds of theorems that play only the degree. But we are lucky to are at SPOC, and we know about polyhedra, so we know about this constraint. So we understand very well why it is not Wissing's theorem, but another conjecture, which exactly in the same way as in Wissing's theorem characterizes or gives a bound for the chromatic number of an arbitrary graph, chromatic index, so the edge coloring number, the integer combination of matchings for an arbitrary graph to be the rounded up fractional part plus 1. Again, this plus 1, the modified integer plus 1, occurs here in this conjecture independently stated by Goldberg and Seymour. And it is equivalent, and actually this is the way Seymour stated it, that for an R graph, the chromatic number is R plus 1. Now, here, even whether this is still a conjecture is an open problem, because a leached proof, as Wikipedia says, was announced by Chen, Jing, and Zhang. You can find in Wikipedia the solution of this conjecture, but it's quite long, 50, 60 pages. And for the moment, it is not fully checked, the proof of this conjecture. Okay, well, this is just a reminder of what is an R graph. And the second conjecture, if there are no minors, then you always have the chromatic number, the fractional chromatic number rounded up. This is a particular property of matchings in these graphs without Peterson minors, which is called the Hilbert basis property. Okay, so note that this conjecture of Lovász contains the four-color theorem, but it is also not forbidden to use it in a proof. So these are the nice problems, and the results are about special cases only, or this result, which is not yet accepted by the community of Chen, Jing, and Zhang. This was about matchings. Let's see now a fourth problem, the bin packing problem, or cutting stock problem. Bin packing problem is the following. You have some real numbers between 0 and 1, which is the size of your objects, and you want to put them into bins of capacity 1. This 1 has no significance. Of course, you can rescale. It just means that we suppose that all bins have the same size in our discussion today. And you want to minimize the number of bins. We know very well this problem, which had all kinds of heuristic and simple heuristics analyzed in a very nice way in the early days of combinatorial optimization. I want to speak today only about this very particular aspect of uniform covers, about the linear program that describes them, and about this Mirup phenomenon that affects them as well. A pattern is a subset of your objects that fits into a bin. Okay, now you can write down a linear program, and Gilmore and Gomori wrote down this linear program that actually can be solved fractionally in a well-known way now with the ellipsoid methods, with a knapsack separation, which is not exact, but here a rounding error doesn't spoil your solution. So fractional solutions can be given. Whatever they are, time is going, so let's just mention the interesting phenomenon that happens here. Can one hope for an integer y here? And actually, in small cases, for instance, Tom McCormick had results that yes, in the two-dimensional case, you can hope for integrality, and more generally, things were not clear until Marcotte in 85 found an example where it turned out that it's not at all true that you always have an integer solution to this LP. Both primal solution, well, the example is that you have one object of size 1/2, two objects of size 1/3, and four objects of size 1/5. The sum of the sizes is 59/30. And this is at the same time the best solution for the primal LP that we had on the previous page, which we can think about as a black box. And the LP, the dual solution, is some easy solutions taken with some very natural coefficients. That's also 59/3. So is the optimum 3 or 2 or 3? Well, it's easy to convince yourself that in this case, this 1/30 place cannot be used by an integer solution. So the optimum is 3. So this is a counterexample to the integer decomposition property for these knapsack solutions. On the other hand, and this is what I want to show because this is simple and takes less time, there's a very nice connection by Romeo Rizzi to the previous problem, to the edge covering problem. And this example is that you take the Peterson graph, and actually you can take any snark, any graph which has similar edge coloring properties to the Peterson graph, and you put the powers of 2 on the vertices of your Peterson graph. Now you choose objects for every edge, and for every edge you choose an object size which is the sum of the two powers of 2 on the two extremities of the edge. For instance, here vertex ig that has size 2 to the power I plus 2 to the power j. And you choose bins maliciously to be the sum of these powers of 2. So 2 to the 10th minus 1. And okay, now what is the minimum number of bins you need for this? 3 or 4? Now, if you want to use bins of this size, of course, you can say these are not 1, but they are all the same size. So they fit into our problem statement. And since you want to fit into a bin, it's only perfect matchings which will use fully your bins. And you would have 3 bins would be enough if and only if you would have a 3-edge coloration of the Peterson graph, but we know that we don't have, so only 4 bins are enough. So there is a quite deep connection between the two, especially that there is a conjecture from 97 by Scheithauer and Terno about the integer optimum being indeed between, again, the linear programming optimum and linear programming optimum plus 1. So this also, and actually this is where the name comes. It comes from Scheithauer and Terno, this modified integer roundup property terminology. So by this conjecture, this also satisfies this. And there are results. I worked on this, and actually we proved it for 7 with quite simple arguments. Some of them are true more generally, but we couldn't arrive the proof of this Mirup conjecture. Now there are results by Karmarkar and Karp with an error of log square the size, and by Klaus Jensen and Solis Oba. There is an algorithm to find optimum +1, but not to prove that this is the linear rounded up +1. And it's quite complicated. So I think a nice solution would also give a simpler and algorithmically more efficient, computationally more efficient solution to this problem. So to summarize, the open problems for 3 dimensions, this problem, this cutting stock problem is not proved to be with 3 different item sizes. You can have many items, but 3 different item sizes. It is not known to be P in P, polynomial solvable or NP hard. And for 8, that's the first number for which this Mirup conjecture is not proved. And it's quite intriguing, this relation. There are 2 ties to edge coloring. The Mirup phenomenon both obey bi-conjectures, but seem to be strongly related. Not easy to find a counterexample to this conjecture. And for one of them, it seems even to be proved. So this Mirup phenomenon and also this example, this reduction of Romeo-Rizzi of the cutting stock problem to edge coloring. Maybe there's more into it. Okay, so we finish with Mirup, and at last, well, let me mention that there are other examples, other Mirup examples that I sometimes forget about, but talking last week with my Hungarian colleagues, Christoph Berzi, I recalled that some conjectures of Rona Haroni and Berger were about common independent sets of 2 matrices, and there were other examples that Ron and other people solve with prove weaker bounds instead of the Mirup bound that they conjecture. They prove a coefficient 2 bound for all these problems. So, and actually, Christoph Berzi proved that packing common independent sets of matroid is an NP-hard problem. So, which is quite recent. It was also not known that maybe you could pack common independent sets of matroid. There was some hope. Now there is no such hope, but there is a hope that this Mirup conjecture could be true for common independent sets of matroids. And we arrived at our last subject, tours. A tour is a spanning Eulerian subgraph of the doubled graph. So it's a 0, 1, 2 vector. It is a graphic TSP tour. This is the same as Michele mentioned, that Gérard Cornuet, Georges Jean-Fonluc, and Denis Nadev called graphic TSP problem. And actually, today, practically everybody who looks at the TSP looks at this problem, which is equivalent to the original TSP problem. So here is such a graph, and here is another such graph, and if you delete these edges, you are still connected, and the parity of the degrees doesn't change. That's also, and for different weights, this may be also the optimal tours. All these examples. Well, of course, for non-negative weights, if it's not inclusion-wise minimal, it won't be optimal. Anyway, these are all tours, and the algorithmic problem that we will not look at today is to minimize the weight. Now, this is the same problem as the metric TSP, as the metric Hamiltonian cycle problem. Why? Because if you have a metric function and you have an Eulerian tour of this kind of graphic tour, a tour shortly, then you can shortcut to get to Hamiltonian cycle. And conversely, if you want to use the Hamiltonian cycle problem for this problem, you take the metric closure. So you introduce for every pair of vertices their distance in the graph with the old weights. Then you find a Hamiltonian, optimal Hamiltonian cycle, and you replace the edges of your Hamiltonian cycle by paths in your original graph. Then the parity of the degrees and connectivity don't change, so you will get a tour in the original graph. So this tour problem is the combinatorial version of the TSP problem. I say combinatorial version because you expect from a combinatorial problem to have an unweighted case as well. And tours and Hamiltonian cycles all have the same size, but tours have an all-one case, and that's an interesting problem. Moreover, you got rid of the metric conditions, which doesn't behave very well for polyhedral studies. So tours are much better, and today all these new results also that I will mention now deal with tours. They go to tours immediately. There is also another problem, the ST tour version. When you when the postman wants to start at a point S and finish in a point T, and there the degree parities must be odd in S and T and even in the other vertices. And that I had to convince myself during long months that it's really a different problem. Okay, now let me introduce the ideas that lead to the use of polyhedra in this matter. And it is a sharpening of the Christofides-Seljoukov 3/2 approximation, the well-known, what you call Christofides approximation, independently found by Seljoukov at the same time, which was just a 3/2 approximation. But three people who know one another quite well, Lawrence Wool, Sybil Cunningham, and David Schmois and David Williamson, different times, they independently noticed that actually 3/2 times the LP optimum is also that not only this Christofides algorithm is a 3/2 approximation, but it finds a tour which is 3/2 times this LP optimum, that Michele called the subtour elimination LP. And moreover, if you have any vector in this subtour elimination LP, then 3/2 times that vector is in the convex hull of tours. Okay. Actually, this is the same thing to say that you can always find a tour 3/2 times the optimum, or to say that for any vector in this polyhedron. This is the same relation as for if you have a minimax theorem for arbitrary weights, then you have a polyhedron. And so if you state an LP bound for arbitrary weights, then you have such a polyhedral result, like the way I stated, which is in this way implicit in their work. They just stated that there exists a tour which is 3/2 times the optimum of LP. But it follows through Farkas's lemma, as remarked by several, by Michel Goemans and Bob Carr also, Carr and Vempala and some other people, Bob Carr, whom we all know from 20, 30 years ago, and who has wonderful observations and also deep results in the subject through the last decades. Okay, now let's just go through the sketch of the proof. So why if you have a vector in this polyhedron, then 3/2 times that vector will be a convex combination of tours. Now, if you have something in the polyhedron, by knowing the convex hull of trees, you know that this vector x will be a convex combination of trees. So in other words, you can choose a random tree with some coefficient, and its average will be this vector x. X half will be a convex combination of fixed parity subgraphs. It will be in the T-joint polyhedron. It will be able to correct the parities of your convex combinations. Actually, I don't know whether Francisco woke up already, but he has very efficient algorithms for finding really this fractional combination of trees and this fractional combination of T-joints. And now, since you have these two things, the sum of a tree, of a random tree, and the sum of a random T-join will be in average 3/2 times your vector. And needless to say that I didn't use anything essential from randomness. You can repeat everything using only convex combinations and also algorithmically to find this 3/2 times the LP solution. Now, there are people who proved a 3/2 minus epsilon randomized algorithm for the general TSP. And they use actually this framework and improve it. I just heard in Bonn a few weeks ago, Nathan Klein, the middle author, speaking about this very nicely. It's worth listening, his talks explaining the result. The paper looks a bit complicated, but it becomes quite human when it is explained. Okay, so let me finish by stating some conjectures. And here the role of uniform covers is to find more abordable versions, more tractable versions of some difficult conjectures. So the first conjecture is nobody wants to be author of this conjecture. It was stated in '76, maybe in the paper of Lawrence Woolsey, but Lawrence Woolsey said, I don't know. You should ask him what he says, whose is it, or where he saw it, or what gave the idea. And it is about this 3/2 that we were working about on the previous slide can be improved to 4/3. So in other words, to any weight of the traveling of any non-negative weights on a graph, you can find for a tour which is 4/3 times the linear programming optimum. And for any vector, which means the same as for any vector in this polyhedron, 4/3 times that vector is a convex combination of tours. So this is an extreme example for this. You have a prism with some subdivided edges and 1/2 on the triangle of the prism and 1 on the paths joining the two triangles. And indeed, if you multiply this vector by 4/3, you can easily, it's a good little exercise. You can leave out one edge of the triangle and double one of the 3 paths. And if you take the convex combination of these, you get 4/3 times the original vector in red. We proved for the distance metrics of graphs. So if you have all one, you take the metric closure of the all one vector, 7/5 times the LP. So that's a bit bigger improvement compared to 3/2. But there was no improvement until the result I mentioned, 3/2 minus epsilon last year. And the thing I stated to make it easier, this 4/3 conjecture, is, and this is this was my first meeting with uniform covers for 3 edge connected graphs. And here you don't need that, you don't need them to be cubic. If you have a 3 edge connected graph, then the 2/3 vector is in the LP polytope, so is in the subtour elimination polytope. And if you multiply the 2/3 vector, right? If you have a 3-edge connected graph, if you multiply by 2/3, you will have at least 2 on every cut. So you will be in the LP, which is not on this side. You will be in the LP polytope. And multiplying by 4/3 the 2/3 vector, you have the constant 8/9 vector. So a consequence of this famous conjecture 1, which looks difficult, is that this constant 8/9 vector is in the convex hull of Tours, can be uniformly covered, and actually 8/9 times, by Tours, a fractional solution. So a fractional solution for the number 8/9 with Tours would give you confirmation maybe that it's or a counterexample to the big conjecture, because a counterexample to this is a counterexample to the big conjecture. And for ST paths, actually, we could prove the analogous conjecture with Anke van Zylen. This 8/9 corresponds to the all-1 vector, and that's the convex combination of Tours. On the other hand, there, the open problem, the big open problem is to have 3/2 as integrated gap, and we have only a bit worse, which was a little bit improved by some 1/1000th by Vera Traub and Jens Wiegen, etc. We are working on these problems constantly, also with Sylvia Boyd, with whom we just, our paper just appeared this year about fundamental classes having better constant bounds, but 8/9 bounds is not reached, and actually the 8/9 may actually not be tight. There might be some better bounds than 8/9. Okay, this is a difficult subject, and many people, and actually PhD theses work on this constant, actually on this small problem, like a student of R. Ravi proved the first bound, which was smaller than 1. I could prove, I delivered with the conjecture the bound 1 also for this 8/9 conjecture, and asked whether somebody can prove smaller than 1. And Arash, Alantha, and Ravi proved the first bound, which is a bit smaller than 1, 17th, 19th. And with Sylvia, we proved better bounds for these fundamental classes, where fundamental means that they are universal, but they are not universal with this property. Okay, now the happy end is that the talk is closed, but the problems remain open. And I repeated 3 of the problems on this last slide. Maybe some of you has already a solution. So thanks for your attention. But I don't hear you. Yeah, you are muted.
Yeah, sorry, excuse me. Thank you very much, Andras. Thank you very much. Thank you for this nice presentation. It's very rich, many problems. Now we need time. There is a conjecture from 76, so we are not going to solve it in 3 minutes. So
there are some more recent ones as well, which have this year.
This is for the grandchildren, maybe. Okay.
That one is for the grandchildren, but there are some more recent ones.
Maybe.
For you.
Okay. Merci beaucoup. Thank you very much. So now we can go straight to the questions. So yeah, okay. So any question, please? We have time for the questions.
Michele is not here. That's the problem.
Yeah, no, he's here.
He's here, Michele.
Yeah. Michele, I have seen him. Yeah, Michele is here. Yeah.
He arrived for the end, so
Michele,
no.
Michele, tu n'as pas une question, Michele? Non, peut-être qu'il a juste la connexion. Et il est peut-être à côté.
Voilà.
Alors, chers amis.
Il
No,
n'a pas
maybe
la
I have a
voix.
question. Yeah, this uniform cover. Yeah, you presented it for different problems for the matchings, for the stable, for the triangle, etc., etc. Yeah, so for any combinatorial structure, we can define a uniform cover.
Pardon, for what?
And for, I mean, for any combinatorial structure.
Yes.
Like, I don't know, like, let's take, you evoked triangles. I can evoke, for instance, dominating set. I can evoke, I don't know.
Yeah, this doesn't mean anything else than whether the all-one vector is in the cone generated by your combinatorial objects. The all-one vector, is it in the cone or not? And usually being in the cone means can be converted to being in a polyhedron. So it's determining the constraints of some polyhedron. But I show some examples where this is particularly meaningful, the all-one function being in the cone, because in the first problem in triangles, graph theorists are very much interested in this uniform covers by triangles. There are many papers about it. In some others, this means the chromatic number. For the TSP, it means it allows us to state a problem which is a particular case of this 40 years old conjecture, and that's only 5 years old or 6 years old. This 8-9 version, which is a particular case. It can be proved from the 4/3 conjecture. It's just one line. It was on my slide, but it does not imply the 4/3 conjecture conversely. So it could be a candidate for having a partial result, something easier before proving the 4/3 conjecture.